Abhradeep Guha. So today we have Abhradeep Guha Thakurta and also Thakkar. Abhradeep is a senior research scientist of Google Brain. His primary research interest is in the intersection of data privacy and machine learning. He focuses on demonstrating that it's possible to design differential private learning algorithm that can scale to industrial workload, both in practice and in theory. Prior to Google, Abhradeep was a faculty at UC Santa Cruz. Before that, he was at Apple and Yahoo, and he received his Ph.D. from Penn State University in 2013. And he was a postdoc at Stanford University and MSR. Thakkar is a senior research scientist at Google. His research is in privacy preserving data analysis, with a specific focus on differential privacy and its application to machine learning, deep learning, and adaptive data analysis. Before joining Google, was graduated from B University and received his PhD in 2019. So today, Abhradeep and will talk about practical and private deep learning without sampling or shuffling. Without further ado, I invite them to start their talk. Thank you.
Sounds good. Thanks, Mariam, for the introduction. What I will do right now is I'll share my screen and let's start from there. And please confirm it works. Enter screen. Okay, sounds good. So just one second. Yeah, so today I'm going to talk to you about my our recent work on practical and private deep learning without sampling or shuffling. It's a joint work with Thakkar, Peter Kairos, Brandon McMahon, Xuang Song, and Zhang Zhu. And I are jointly sharing the talk. To start with, just one second, I'm getting some feedback from my computer. I don't know why. I'll probably leave from here. So, sorry, one thing I wanted to say is that I can't see you. So if you have any questions, please speak up, then I can hear, because I'm just having one screen. Okay. So yeah, so to start with, the algorithm which we'll start with is what is called differential private stochastic gradient descent. The history of this algorithm goes far back to 2013 by Song et al. And then there was a paper by Raif Vasili, Adam Smith, and myself in 2014. And there was this paper by Abadi et al., which kind of stabilized this whole algorithm. What we know today is to be stochastic, DP stochastic gradient descent. So to set the stage, you have a data set of n elements, and the algorithm works as follows. You sample a mini batch of size k, compute the gradient at a current model theta t on this mini batch, and add some IID Gaussian noise from standard normal, and you do exactly as if you do stochastic gradient descent, excepting what you do is you add this noise to the gradient and you update with this noisy gradient, and you run this process for t steps. Okay, so this is the high level / cartoonish view of stochastic gradient descent with DP. Now, to start with, to kind of set the stage, like why, what kind of guarantees we are looking at. So if you want to get differential privacy guarantee, let's say constant differential privacy guarantee, your standard deviation of the noise would have to roughly scale as square root of t, where t is the number of steps you are taking, over k, where k is the mini batch size. If the mini batches were chosen arbitrarily, that is, you just pick a mini batch from this data set T and just run the gradient. And this is not surprising, because if you are computing the gradient of a mini batch of size k, and if your loss function is, let's say, Lipschitz, then your sensitivity of this gradient query is in the order of 1/k, and you run the process for t steps. So you pay this extra square root of t factor because of composition. Now here is this tool called privacy amplification by sampling, which allows you to get this error down to square root of t over n. If the mini batch of this size k were sampled uniformly at random. Of course, I'm hiding a lot of factors and a lot of caveats here, but the important part here is that the scaling of the standard deviation. If the mini batches were chosen arbitrarily, your the amount of noise you need to add is in the order of square root of t over k, versus if the mini batches were sampled uniformly at random, then you would have to add noise in the order of 1/n. Okay.
I have a question.
Yes, please.
So when you're saying the manufacturers are chosen arbitrarily, what does that mean? It doesn't mean that you reuse the data, or so what is the difference when you're saying arbitrary versus random? What is the difference?
Oh, so what is the difference? So you can think like your data set, let's say your data set, you take the first k samples from your data set, that's your first mini batch, next k samples is your next mini batch, and so on and so forth. So there is no randomness in the selection process.
So the data could basically in a sort of an adversarial order. And
precisely.
And if, okay.
Precisely. So you, in particular, you don't make any assumptions in the ordering of the data. Good. Now, okay. So another point is that you have this 1/k versus 1/n. Clearly, mini batch of size k is much smaller than the full data set size. So amount of noise you need to add is much higher, at least theoretically. Here comes the main question for the rest of the talk. Sampling reduces noise for the same level of privacy when the mini batch size is much, much smaller than n. And the question is, can we avoid sampling in situations? And I will give motivations for it. This gap between when you are sampling, when you are operating with a mini batch size of size k versus n, and you are looking at the privacy cost for sampled dPhD, where your sampling is done uniformly at random, versus unamplified dPhD, where you're just choosing the batches in an arbitrary way. It's not just a theoretical artifact. Even if practically, if you look at the privacy utility trade-off, the privacy utility trade-offs are way, way off for unamplified dPhD. And this is a run on Cipher 10. Cipher 10 is a vision data set which people typically use for benchmarking tasks for deep learning. Okay, so the point is that it is not a theoretical artifact, the problem is real. Okay, now why are we kind of harping on this fact on privacy amplification? Well, in a lot of situations when you have full data set in your control, you may actually do uniformly at random at each step of the training process. But in variety of settings, in particular in federated learning, it is either hard or it is impossible to do privacy amplification by sampling. Simply because if you look at this picture, the availability of the devices or the let's say cell phones vary with time and day. Now, even if you want to sample a mini batch of, let's say, size k uniformly at random from the whole population of devices, it is just not possible because many of the devices either would not be ready to give you data, or they are not connected to Wi-Fi, or they are switched off. So you don't have control over your data to sample from. So in that kind of situations, the whole structure of privacy amplifications by sampling actually falls apart. Even in centralized setting where you have a central data source where the data set is lying at the server, it is still highly non-trivial because sampling at every round of the training process is very expensive. And it's not that you have to sample every epoch or something, it's sampling at every step of the training process. And typically you require 5,000 to 10,000 steps for this kind of training processes. So first thing is that. Second, to my knowledge, almost all deployed systems or code bases which are out there in the public for doing dPhD do not implement privacy amplification by sampling. the punchline is it is hard to implement in practical, and of course in federated settings it's almost impossible to implement unless you make like non-trivial changes to your system to kind of do these things. So what is this talk about? Can we avoid sampling and achieve similar privacy utility trade-offs? Or in other words, can we operate over datasets where I'm not relying my privacy guarantee on the randomness given by the sampling procedure? Before I go to the next part of the talk, it might be worth pausing a bit and asking questions. If there are any questions for the motivation at least. Okay. So let me go to the next part of the talk. So first thing I wanted to say is that any conclusion which I'm telling about sampling also holds for privacy amplification by shuffling. For people who know about shuffling, the papers which I'm referring to is like Arlington et al. And Pellman et al. Whatever I tell for sampling would make sense there too. And people who don't know about shuffling, just ignore this part. Okay, so here comes the structure of the talk. In the first part, it will be mostly boilerplate to talk about differential privacy and empirical risk minimization. The second part would be about the actual algorithm which we'll use for getting rid of this privacy amplification by sampling. And the third part would be mostly theoretical guarantees for this algorithm. And in fourth part, which will be handled by Om, to actually delve deep into the empirical evaluation of this algorithm. Okay. Probably this is mostly for completeness purposes, but for this audience, I don't think this definition needs introduction. What I would still point out are two properties of the definition. One is composition, meaning that if you have T algorithms in sequence and each of them are epsilon dp, then by composition, you would have epsilon square root of dp for the overall process. So that's one thing. And second is this amplification by sampling, which says that given a data set D, if I have an algorithm which is epsilon differentially private on this data set D, if I sample each element of D with probability Q and run the same algorithm on this data set D hat, then my algorithm is Q times epsilon dp. Of course, there are other factors on epsilon which I'm pushing it under the rug for brevity purposes. But the fact is that if you do sampling with probability of Q, each of the data sample, then your privacy gets enhanced by this factor of Q. And this is not surprising because in a data set, if I change one of my data sample, if I sample with probability Q, that data sample which actually changed with probability Q only it shows up in the data set D hat. So that kind of, I mean, if you work at the math, that would give you amplification. So these are the two properties of differential privacy, which I wanted to kind of remind, because for the rest of the talk, we'll be using them as and when needed. Okay. The second part is mostly about the main problem we are looking at is empirical risk minimization. A classic example is linear regression. So what you want to do is, suppose you are given data samples from some distribution, tau, X is the feature vector, Y is the response, and you want to minimize the population risk, which in this case is Y minus X theta whole squared. And you want to output a model under differential privacy, which approximates theta star. And for the purpose of the talk, I will use the population risk as calligraphic L, which is the expected loss. So what does private empirical risk minimization does? It outputs a model theta priv with the low excess population risk. So that's my objective in terms of accuracy. So the algorithms which I will design will be first differentially private, and second, it will minimize the excess population risk. Okay. So another concept I would need here is online learning. The motivation for this kind of this framework is that, remember in the initial part of the talk, I was telling that we will not use amplification by sampling. And the fact that we will not use amplification by sampling would kind of guide us towards algorithms designed based on streaming or even adversarially chosen data. And the classic framework we would use for handling those kind of settings is online learning. So what's the idea in online learning? So you can think it as a game. At every time step, the algorithm outputs a model theta. It looks at a data sample t, pays the price of the model theta at data sample t. Again, it looks at the loss, outputs a model theta 2, gets a d2, pays the price at theta 2, and this process continues up until it has seen n samples. Two things to notice is that the data sample di is chosen after it has after the adversary has looked at the model theta I. Okay, so this is the classic online learning setup. How do you measure the quality of an online learning algorithm? You measure in terms of what is called regret. What it says is that how does my algorithm perform in comparison to the best model in the hindsight? What I mean by that is, remember that at every time step t, your algorithm pays a cost of L theta t at dt. And you are comparing the cumulative error, what you're seeing overall, in comparison to a model theta star, which would have been chosen if all the data samples were given to you at once. So suppose I give you all the data samples d1 till dn at once, and I would ask you to choose a model theta star, which minimizes the average loss over these data samples. I will compare the performance of my algorithm in comparison to that particular loss. Does it make sense? A closely related notion of regret, which is called stochastic regret, which says that I will have the same thing as adversarial regret, where the data samples come in streaming order, excepting that these data samples d1 till dn are chosen IID from some distribution tau. So it's a slightly weaker version of the regret. In adversarial regret, the data samples d1 till dn could be chosen adversarially based on what the adversary is seeing in terms of the model output by the algorithm. In stochastic regret, it is chosen IID from some distribution. For reasons I will not get into this talk, both adversarial regret and stochastic regret would give you the same bound on excess population risk, at least in the context of the problem which we are looking at in this talk. Hence, to bound the utility or the accuracy of our algorithm, what we will design, we'll just focus on regret guarantees. Because it will be, I mean, once you get a good regret guarantee, that would immediately imply excess population risk. Question?
Yes, Abhradeep, can you just go back to the definitions, please?
Yes.
Okay. So is any of these in the batch framework, or they're all online?
Right now, whatever I've said is completely online.
Okay. Thanks.
And the idea would be that I will use this online framework to get guarantees for the batch algorithms.
Mm-hmm. Mm-hmm. Okay, thank you.
So now this talk will be about regret guarantees. And now comes the main crux of the talk, which is the algorithm. The algorithm what we will use is what is called differentially private follow the regularized leader. Just to remind the audience about DPHD or differentially private stochastic gradient descent, you have a data set of n samples, you take a mini batch, compute the gradients, add noise, and do state updates. And we say that if the mini batches were chosen arbitrarily, then you have the noise in the order of 1 over k, where the k is the mini batch size. But if it was sampled uniformly at random, you pay in the order of 1 over n. And I said that the problem is real. Even in practice, you can see this gap between amplified versus unamplified DPHD. Here comes the algorithm. The The foundation of our algorithm is based on what is called follow the regularized leader. It is a very, very well studied algorithm in the online learning literature. It traces back even before the citations which I've given. I've mostly missed out citations on this, but the earliest which I can think of is McMahon 2010, then Ducci et al. From 2010 and Lin Xiao from 2010. There are various names in which this algorithm was proposed. It's either called follow the regularized leader, dual averaging, and other variants. So the algorithm is as follows. What you do is at every time step t, you take the cumulative loss on the data samples you have seen so far. So it's like almost the history of whatever you have. Treat that as a data set and minimize this cumulative loss. And that's your theta t plus 1, the t plus 1th update, accepting the fact you add a regularizing term, which is lambda over 2 theta squared, the L2 norm of theta squared, to kind of stabilize for the future. Because really, if you look at this picture, your theta 1 is not played with. Yeah, so the point is that the model which you're outputting does not know the next sample. So you are playing the model which you're outputting at time step t with the next sample which you are seeing. So you have to kind of make sure that you are not too much tied to the history or all the data samples you have seen up until now, but you want to actually do well on the next data sample you are seeing, and that's what this stabilizing term gives you. So the first term is the empirical loss at time t. The second term is the stabilizer to the new data sample at time t plus 1. Okay. And this is the FTRL algorithm. Excepting you just make a mild adjustment. The reason is because if I were to solve this optimization problem at every step, I'm solving a convex optimization problem at every time step. Instead, I would make the problem slightly simpler, and I would actually solve what is called the linearized version of the problem. What I mean by that, if you look at this particular picture, if L of theta is a convex function, you draw a straight line or the tangent at the model theta I. Since it's a convex function, this line always lies below the function, and it touches the function at theta I. This is just the first order Taylor approximation of the loss function. And since this linear approximation lies below the function, so instead of using the loss function, if I were to use this linear approximation, I only upper bound a larger object, which means that linearization only increases the regret. So if I can bound the regret on this linearized losses, I immediately bound the regret on the original loss functions. So from now on, I would just operate with the linearized loss. So my loss now is, instead of L of theta I at di, it is the gradient of L of theta I at di. So this is a non-trivial jump which I made. Instead of playing the actual loss function, the algorithm would actually use the linearization of the loss function for the optimizations process. Okay. In the literature, this particular version is called the follow the regularized leader typically. Now, our objective is to design a differentially private FTRL algorithm. So let me try to state it in a way which is which would look familiar to the differential privacy audience. So now look at this algorithm, the FTRL algorithm. At theta t plus 1 is estimated as, I'm estimating the gradient, adding up the gradients from I equal to 1 to t, and I'm minimizing this regularized loss. Where gi, and here I'm just for brevity purposes, I'm saying gi is the gradient of the loss on data set sample di at model theta I. Right? Good. So to solve this problem, at every time step, all I need to compute is a bunch of what is called prefix sum in the DP literature. Is that in the first time step, you have to compute G1, which is the gradient of the first sample. In the second time step, you have to compute G1 plus G2. And in the nth time step, you have to compute G1 till Gn, summation of that. Since I can't see you all, I hope this translation is clear. Okay. So now, once I have stated the algorithm in this particular way, Now we can use our favorite machinery from DP literature, which is the tree aggregation algorithm. So essentially what you will do is you will use this tool. I haven't told you what this tool is. Om will spend quite a lot of time on explaining this tool. So there is a classic algorithm called the tree aggregation mechanism, which dates back to Dwork, now Pitasi Rodblum from 2010, and the paper, contemporary paper by Chen, Song, and Shi from 2010. The adaptive version of this particular algorithm showed up in this paper of myself and Adam Smith from 2015, and there was an improvement by Honecker in 15 on this particular algorithm. The point is, there is a machinery, like a really strong machinery for computing these prefix sums in a differentially private way. And that's all I need for my FTL algorithm. Once I can feed in my differentially private estimates of this prefix sums, I'm good. So instead of feeding in the cumulative sum of the gradients to the algorithm, I would actually feed in something which is output by this algorithm, a tree, which is the tree aggregation algorithm. Now, I will not give the details of the algorithm at this part. Om would talk about it more, but just to kind of set the context, this algorithm ensures that under epsilon delta differential privacy, the error of the tree aggregation algorithm on the cumulative sum versus the true cumulative sum is in the order of log n over epsilon. Just to kind of put things in context, if you use standard composition, you'd only get like square root of n because you are making essentially n queries. But whereas if you use this cumulative sum structure and use the tree aggregation algorithm, you can get away with paying only log n cost. So what are the properties of the algorithm? I told you about a streaming version, like you say one sample at a once and you design the algorithm. It can be trivially extended to mini batches of size 1 and greater than 1, and also to more than one epoch. You have to just make sure that you are accounting for the sensitivity in the right way. What is not obvious from what I've showed, but it is not hard to see if you actually kind of open up the recursion of the SGD process. If you're doing unconstrained optimization, this updates what you're getting from tree aggregation and DPFTRL is equivalent to that of DPSGD if the noise is drawn from the tree aggregation algorithm. So you are essentially adding some kind of a correlated noise at every time step. And this is a non-trivial statement. So in DPSGD, what you do is you sample the noise independently at every time step and then just add noise to the mini batch gradient. But if you take this FTRL, follow the regularized leader view of this DPSGD, you will see that the updates look very, very similar, except in the fact that the noise at time step t is dependent on the noise at time step t minus 1. And the way it is correlated is via the tree aggregation mechanism. The third observation is that if I compare to amplified DPSGD, where I'm using privacy amplification by sampling, the noise per update is off by a factor of polylog n, at least theoretically. So essentially now what this the third bullet actually tells me to do is that I have brought myself almost at the ballpark of differential private stochastic gradient descent with amplification by sampling. Of course, I'm off by polylog n, but hopefully in empirical settings, this might not matter that much. But notice that the algorithm, this DPFT algorithm, neither uses amplification nor it is using any property like data shuffling or anything. It just can operate over like almost adversarially chosen stream of data samples. Right. One thing I wanted to mention is that the idea of DPFTRL is not new to the paper which I'm talking about, but the main idea actually showed up in a paper of mine and Adam Smith from 2013, except in the fact that in that paper, we used a quadratic approximation to the convex loss instead of a linear approximation, which I'm using it here, which made the algorithm much more complex. The earlier algorithm much more complex, and also it had suboptimal guarantees when you are dealing with unconstrained optimization and so on and so forth. Okay.
So there is a question in
Yeah.
chat.
Please.
basically, so okay, sorry, I'm gonna read it. So the reason we can't combine the tree-based mechanism with the subsampling is because in the subsampling setting, the mini batches won't be destroyed, right?
Yes. Yes. Yeah, but there are ways of combining subsampling with tree aggregation in the sense that you can first subsample a sufficiently large chunk of the data and then use tree aggregation on that chunk. But the precise reason, the vanilla combination of tree aggregation with subsampling does not work, because in subsampling your mini batches can kind of overlap, whereas in tree aggregation it should not.
Got it. Thanks.
Okay, so now going to the third part of the talk, which is the regret guarantee. Okay. So again, recall, we are looking at two types of regret: adversarial regret and stochastic regret. In adversarial regret, the data samples come in a stream, and the data samples can be chosen adversarially by the adversary, whereas in stochastic regret, these data samples are drawn IID from some distribution. And as I told you, both adversarial regret and stochastic regret would lead to the same bound for population risk, at least for the context of this problem. Okay, so the first error. If the optimal model is theta star, meaning that the hindsight model when you have the complete data, then you can get an adversarial regret in the order of 1 over square root of n, where n is the number of data samples, plus p is the number of dimensions in the model space, p to the power of 1/4 over square root of epsilon n. The first term is the non-private optimal error. You cannot get out, you basically cannot avoid that. The second term is the more interesting one, and the question is that, is this optimal? Before talking about that, let me tell you what are the improvements in comparison to Smith and Thakurta 2013. It makes a small improvement over epsilon, going from epsilon squared to epsilon, mostly because of the tightness of the analysis. The first improvement is just because of the tightness of the analysis. And the second thing is that it allows unconstrained optimization because of the fact that we are making linear approximation to the loss rather than quadratic approximation to the loss. Now, one open question for people to think about is this regret bound tight? This is the best known regret bound for online DP-ERM algorithms we know of today. But the question is this bound tight? What I will show next is that in restricted kind of problem settings, we can actually get better bounds. If I'm dealing with linear losses, suppose my loss functions were linear or it was least squared loss. What I mean by that is, like, you do linear regression, let's say, I can get the error down, the second term due to privacy, from p to the power of 1/4 over square root of epsilon n to square root of p over epsilon n. And we know that this bound is tight. And when I said open problem, the question is for, can we get similar guarantees for general convex losses? And that's the open question. The bound which I'm showing here is not new for linear losses. For least squared losses, this is new. For linear losses, it is not new. There was a paper by Naman Agarwal and Karan Singh from 2017, but their algorithm was designed on something called follow the perturb leader. And by the nature of that algorithm, it cannot get high probability guarantee. And what I'm showing you here is a high probability guarantee. Open question, can you achieve similar bounds for general convex functions?
Abhradeep,
Yeah.
Can I ask a question? I don't know if you can hear me.
Yes. Yeah.
Can you give us a sense of what the obstacle there is for general losses? Is it
yeah. So so the main issue is that the analysis what we know of so far is that, like, the gradients what you are getting, right? So if you are dealing with linear losses, the gradients don't change with time. In particular, the gradients don't depend on the models, right? So so if you're dealing with linear loss function, the gradient at time step t is dependent just on the loss. It does not depend on the loss at a particular model. So there is this adaptivity which shows up in general converse functions, which kind of makes things harder.
And that doesn't show up with quadratic losses because the dependency is very simple or something?
Yeah, so what I can do is for quadratic losses, I will, I cheated here. The statement to prove this kind of a statement, you will not only do cumulative sum on the gradients and the linear term, you'll also do a cumulative sum on the covariance terms.
Oh, but doesn't that change the dependency on the dimension?
No. Because you are dealing with Lipschitz losses, right? So you are assuming that the feature vectors are normal bounded.
Right, but doesn't P then become like P squared, like the dimension of the quadratic of the Hessian? Wait,
No,
maybe I
but,
misunderstood what you said.
Yeah, so I'm saying that the dimension becomes P squared. Yeah, you are dealing with a P squared dimensional object, but essentially you are dealing with the inner products right there. So the point is that it does not.
So here, even with quadratic losses, P here is the dimension of the parameter vector,
Yes.
not the dimension of the Hessian.
No, no.
Oh, okay, that's cool. Thanks.
Okay, so putting things in context, this is the best known excess population risk for a single pass algorithm that does not rely on convexity for privacy. So every word in this sentence matters. It is a very carefully chosen sentence. You should treat it as almost as a legal statement. Okay. First of all, I'm looking at a single pass algorithm right now. So I'm not traversing the data multiple times. So it's a single pass algorithm. Anything that improves on this d to the power of p to the power of 1/4 over square root of epsilon n, what we know of today, either does a multipass algorithm or it heavily uses convexity for privacy guarantees. What I mean by that is it will use things like privacy amplification by iteration kind of arguments. And why am I kind of highlighting this point is that ultimately theory is good for this kind of problem, but ultimately we are going to use it for deep learning settings. And if I'm relying convexity for privacy, then I cannot do that. Okay, so just to set the context, the best known bound for the population risk for private ERM is 1 over root n plus root d over epsilon n, but it does heavily use convexity for privacy and hence cannot be used for deep learning settings. So that's the reason of the quantification here. Now I will stop my sharing and Om will take from here.
Thanks, Abhradeep. Let me just share my screen. Okay, is the correct screen visible to everyone?
Looks good.
Awesome, thank you. Yeah, so now I'll cover the last part of the talk, which is how does a DPFTRL compare to DPSGD, both amplified and unamplified in practice. So we start by understanding privacy amplification by sampling from an FL perspective. So imagine a distributed setting of devices that you want to train over. And as Abhradeep covered earlier, each round of training, we will take B random users that participate in this round, and we add noise to their updates to proceed to the next round. So the goal here is to hide the effect of any particular user. And in this setting, there are two sources of randomness. The technique I'm describing is called differentially private federated averaging. The same applies for DPSGD. So one source is you add noise to the updates, And the second source of randomness is uniform sampling of users. And the high-level understanding is, in each round, a user has a limited chance of contributing, which amplifies their per round privacy. And this is composed over the number of rounds that you carry out training. If you look at a practical setting, such amplification is infeasible because all users should be capable of participating at every round. And there are other challenges which we highlight in this paper. It also provides a feasible way to do this, but it requires complex changes to systems. So now, what do we do? The first question could be, why can't we use this TP federated averaging without amplification? And the short answer is the privacy utility trade-offs that we get are significantly worse. So on the right, I'm showing a plot that shows the privacy utility trade-offs on Stack Overflow dataset. So it is, we train a language model for next word prediction. And on the y-axis, I'm showing the performance of the model, the utility, which is denoted by test accuracy. And the x-axis is privacy level. The dotted line is DP federated averaging with amplification, and the solid line on the bottom is without amplification. So as we can see, for any particular privacy level, the performance of DP federated averaging with amplification is significantly better. You get improved utility at the same privacy. Yes.
Am I reading this correctly, though, that the test accuracy is very, very low?
Test accuracy is so there is
bigger number is better.
A bigger number is better. Yes.
And we're getting numbers like 18, 19.
Yes. So this is the setting of next word prediction. So given like the so our non-private accuracy that we get here is like close to 19 or 19.5.
I see. Thanks a lot.
So as epsilon increases, we approach the non-private baseline, but otherwise it's much lower.
Did you say that the next word prediction accuracy is 90?
19.
What is
19?
19. I see. Okay.
Yeah.
Good. I was just a little sorry. I was confused. That makes more sense. So these are both approaching the kind of non-private baseline, but only with very large values of the parameter epsilon.
Exactly.
And the epsilons are always greater than 1.
Sorry, I couldn't hear the question.
So, so if in the horizontal axis, it says user level epsilon. So it says it seems your epsilon is always greater than 1.
So
that I'm a little bit confused is that because early on we were, I think we were concerned because we wanted to make the epsilon squared and bring it down. Like one of the improvement compared to the previous paper was basically bringing down epsilon squared to epsilon, and I think it is less interesting if epsilon is larger than 1. Like 1 over epsilon and 1 of, am I clear what I'm trying to say? It's like your theoretical results will be more interesting in the small epsilon regime. But here it seems like everything is above 1.
Yeah, that's a great question. So we are showing the performance for small epsilon, but as you can see, like the leftmost point, if you compare the accuracy, it is significantly worse than what you would target without privacy. So the trade-off at that point is really bad in terms of utility. So even though the difference between the amplified and unamplified is very large, essentially both of them are doing really bad compared to the non-private baseline. And as you increase epsilon, yes, the effects of sampling or the advantages of sampling reduce, but you get closer and closer to your non-private baseline. So here the trade-offs are significantly worse for like really small epsilon, mainly due to like it being a user level guarantee and like the size of the data set and so on.
Thank you.
Does that answer? Okay.
Yeah, and then, sorry, one more question. So, okay, so this is a user level acceleration. Nothing. Thank you.
Yes, so this is with respect to a user as opposed to one record of a user. So it's a much stronger granularity. So now I'll explain the tree aggregation technique that Abhradeep described earlier. And to do that, let's understand what happens in DPSGD first. So the only components that depend on the data are these gradients, which I denote from G0 to Gn. These are the gradients per round. And as we know, DPSGD adds IID noise to each such update. So if I consider this in a streaming setting, when I get G0, the technique adds IID Gaussian noise, makes it private and releases that for the next update. When I get G1, it does the same, and so on and so forth. So for every subsequent update, the technique adds independent noise and releases it for the next round. And as we saw earlier, DPSGD without amplification, if I compare the total noise added to the final sum, it scales with √n. Whereas if you use amplification, you can get a much better guarantee. The overall noise is 1 upon epsilon, which is significantly better than √n upon epsilon. Now, what is tree aggregation? And I'll describe this using the figure on the right. So when we get the first gradient G0, we just release it with adding IID noise. But when I get G1, notice that I can form this tree structure that I show on the top right. And what I instead release is the sum of G0 and G1 with IID noise. So instead of 2 units of noise that would show up in DPSGD, here I'm just combining the sum and releasing them with a fresh instance of noise. Proceeding further, when I receive G2, I do what I was doing in DPSGD, like I take a fresh unit of noise and release it. But now when I get G3, I can now use my tree structure to get a new node on the top, which is the sum of these 4 gradients and a fresh unit of noise, and I can release that instead. So since I only care about prefix sums, I can use this tree structure to reduce the noise that I add in the overall cumulative private sum. So is the aggregation clear? Are there any questions at this point?
I have a question. So how exactly does the tree aggregation allow you to reduce the amount of noise? Like properties? Is it the sensitivity or what's happening there?
So it uses the structure of the technique that at every point you are receiving a new update, and you just need to hide the influence of that update in the prefix sum. So when G3 arrives, I could just add noise to it and release that as the private estimate. But instead, what I do is I use the previous actual gradients, I sum them up and add a unit of noise. So overall, if I compare what noise was added to the prefix sum, I can save a factor in that, and I'll just describe next how much is the savings.
Okay, thanks.
So if you see here, the bottom row of the tree represents what DPSGD would do. So for each gradient, it would add noise and just release the sum of those. Whereas in tree aggregation, I can get away with less noise by releasing the roots of subtrees. So instead of releasing the bottom row sum together, I can just release the top node, and that contains much lesser noise. So what does this buy you? Abhradeep already gave a comparison earlier, but this basically gives you the final noise, the noise added to the final model scales with root log n over epsilon. So the first observation is if you use DPSGD with sampling, you get 1 over epsilon, whereas here it is closed, it is root log n. But crucially, there is no sampling requirement. We didn't place any assumptions on what order the data was received in. And furthermore, you can reduce the variance in estimation using work from Honecker 15. So you can save in constants using previous estimates. So you can reuse previous estimates to reduce the noise in your final answers. Now, in terms of space, how does this compare? Because in DPSGD, you just added noise to a gradient and released it. So you just needed the space for a single update. In this DPFTRL approach, you don't need to save the whole tree. At any point, you can get away with storing only log n nodes. So with a log n increase in the space requirement, you can essentially let go of sampling, and you get this guarantee that is polylog worse than DPSGD. So now, what do we get in terms of empirical performance? So first, I'll show the results for Cipher 10. In the paper, we have results on 2 more data sets, but this is representative of the trends that we see. So there are a lot of things in the plot. I'm showing test accuracy versus privacy, as I was showing earlier. The orange plot is DPSGD with amplification. Yellow color denotes DPSGD without amplification, and violet shows the performance of DPFTRL. And for the latter 2 techniques, we are showing 2 variants. The solid lines use the same size mini batches as DPSGD, and the dashed lines show an increased computation. So what if you were to compute with 4 times the mini batch of DPSGD? And the understanding is, as you increase the mini batch size, you are giving more compute to each technique, and your privacy utility trade-off should improve. See here, the first thing that we see is that if you don't use amplification, DPSGD performs poorly even with large mini batches. So even at 4x the compute cost, it just matches, it's close to the performance of DPSGD with amplification. So the dotted yellow and the orange plot are close if you compare with high epsilons, but it's still poor at low epsilons. The second observation is as you increase epsilon, DPFTRL performs even better than DPSGD with amplification. So the crossover point here is around epsilon 6, but beyond that, DPFTRL provides a better price utility trade-off than SGD with amplification. Furthermore, if you allocate slightly more compute to DPFTRL, it outperforms DPSGD with amplification. So if you compare the dotted violet line and the solid orange line, you can see that it always provides better privacy utility trade-offs. And this is allocating it slightly increased computation, and we can let go of the assumption of sampling. Any questions?
Yeah, I have a question. So there's no dotted version of the red line. Is that because it's basically the same, or?
Great question. So if you allocate increased computation to DPSGD with amplification, you should get better trade-offs as well. But the point here is solid orange is kind of unachievable in realistic settings. So what we are saying is, if you set that as your baseline, what would you need to do to get performance that matches DPSGD?
You're saying even solid orange is very hard to implement for all the reasons you mentioned. Never mind dotted orange. I see.
Right. So solid orange is what is like state of the art, and we want to match the performance of that, but we cannot achieve it in realistic settings. So now what would it take to match that performance? And with DPFTRL, we see that as epsilon increases, you can match the performance or get slightly better. And if you allocate some more compute, you can very easily beat that performance. Does that help?
Yeah, that helps. Thanks.
I also have a question about, so the orange line, there's not exactly a batch size because you're like sampling. So, but like the expected batch size, but is that comparable to the solid purple line, or is it comparable to the dotted one?
Yes. So all dotted lines have the same batch size, which is 4x the batch size of the solid lines, and all solid lines have the same batch size. Yes. So they are basically at the same computation level. That's what we are trying to equate here.
Okay, thank you.
I have a question too. Do you have a sense for why the test accuracy kind of levels out at 70%, even for really high epsilon?
That's a great question. And my current understanding is for Cipher 10, the trade-offs are such that we have to go to a really high epsilon to get the non-private baseline performance. At low epsilons, we are really far from the non-private baseline. And this is like the size of the data set is 50,000. The model size here is, if I remember correctly, it's close to 1 million parameters. But yeah, basically the trade-offs are not great for Cipher 10. as compared to, say, if you were looking at MNIST, which would regain the non-private baseline around these epsilons.
Okay, so it's something inherent to the problem, I guess,
Yes.
before. Okay. Any other questions?
Okay. Thanks for the question, and feel free to ask.
So let's think Abhradeep for the first.
Oh, I actually have 2-3 more slides. I don't know how am I running on time.
I'm so sorry.
Yeah, you've got another couple of minutes. I mean, we're running a little over time, but you've got another few minutes.
Oh, I see. Okay, I can run it quickly then. I thought we had until like okay, great. Let me just
More pictures are good. Yeah, show my
yes. So basically, this is the trade-off on Stack Overflow. The yellow plots we saw earlier, but the blue one is DPFTRL. So it performs SGD, outperforms SGD without amplification. At low epsilon, it is competitive. And at high epsilon, it beats SGD with amplification. And the two effects here are basically as you increase epsilon, the amplification is decreasing, that the power of amplification is decreasing, but TPFTRL does not rely on any amplification at all. That's why it's like constantly providing a better and better performance. The way to understand it, it's like an application of the Gaussian mechanism, and so like a side effect is it can also get a ZCDP guarantee, which the other two, like with amplification, cannot. So what next? One direction that we think would be useful is merging DPFTRL with adaptive clipping, which typically saves in hyperparameter tuning. Currently, it's working with fixed clipping per round. Binary tree aggregation may not even be the best way to aggregate prefix sums. And this is a plot from a more recent paper from Abhradeep, Brendan, and Keith Rush, which shows that at dyadic intervals, you get a lot of buyout. So like when you aggregate the tree and release the root node, you can see that the variance of the noise that you add decreases, but in general, it can vary a lot. Whereas the new paper designs a better aggregation approach for prefix sums, and the blue plot on the bottom is showing that. So the noise added is much lower, and even variance is like much lower. And so we started with, can we avoid sampling and achieve similar privacy-related trade-offs? The short answer is yes, we can. This is the end of the talk. Thanks a lot.
Thank you. Any final questions? Thank you. Yeah.
Sure. Yeah. Thanks very much, Om and Abhradeep, and everybody for coming. You know, it's too bad we couldn't get you here in person, but this is the next best thing for now, and that was great. So hopefully you'll make it to Boston in some future iteration. And our next talk is how soon? Not
I
for
think in March 21st.
March 21st. So